Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. Ladies and gentlemen, let's continue our computational fluid dynamics CFD tutorials. In this short video, we're going to investigate the convection heat transfer in ANSYS Fluent and ANSYS Thermal Steady State Thermal. We're going to use a very simple geometry. Let's see. There is a pretty high confusion when we use the convection in ANSYS Steady State and Fluent. Simply in ANSYS Fluent, we have here temperature boundary conditions. So when a fixed temperature condition is applied at the wall, the heat flux to the wall from a fluid cell is computed as, here is Q, and we have here HF fluid side local heat transfer coefficient for the moving fluid, and we have here the wall surface temperature and the local fluid temperature, and we have here Q radiative heat flux. Okay, but we're gonna use focus on the term of this. The convection here is HF, and here the wall temperature minus the free stream temperature or the local fluid temperature. If you have a simple geometry like this, we have here aluminum, it's solid, and we have here an air duct. Okay, I'm just using an air duct to be able to solve this in Fluent, because Fluent focuses on or mainly focuses on the fluid domains. So we're going to investigate this case without any convection heat transfer to this surface and see the temperature, and then we're going to add convection heat transfer by two methods, okay, by changing or many methods, and then we're going to compare that to the ANSYS steady state thermal. So we have here in Fluent, I'm gonna skip the meshing and these kind of things we have because it's pretty easy. You have general here and models, just energy on and viscous laminar. Okay, we no problem with these kind of things. We have here aluminum, and we have here cell. Aluminum is gonna be solid. This, and the fluid is gonna be air. Okay, for the boundary conditions, we have inlet and outlet. I have the inlet at the bottom, and the outlet, this face is the outlet of the air. Okay, but before we do that, we have here to put the gravity, negative y direction. Okay, it's negative y direction. We have here this red face is the outlet, and the bottom face, this blue face, is the inlet of the air. Okay, it's a pretty easy case. Now for the inlet to the laminar, we're gonna use as a default 0.1 is a small value, thermal 300 Kelvin. Okay, for the outlet, pressure out 0 gauge, and thermal, okay, 300 Kelvin. Now I named this face in the meshing as thermal wall to just set the boundary condition of it. Zero heat flux. Now in Fluent you can add heat by many methods: the heat flux, or temperature, or convection, radiation, or mixed or vice system coupling. We're gonna investigate the convection in this case, but now we're not gonna use anything. Just leave it alone. Leave it as it is. Simple Green-Gauss cell base, second order. We're gonna initialize that. Okay, let's see the temperature. And run calculation, because it's a very easy case. It is not gonna take time the convergence occurs fastly or quickly. Okay, just in a matter of seconds, we have here the contours for the interior aluminum interior fluid. We have, when we want to see the temperature for the interior, as you can see, any temperature here is just 300 Kelvin. Why? Because there is no heat transfer between the aluminum and the air duct, because the air enters at 300 Kelvin and no heat transfer. So the aluminum, this means that the aluminum will take the temperature of the air duct. Okay, so this is the very easy case. Now we're gonna investigate the convection. If I add convection to this surface, while I'm gonna let the other setup or conditions, they are the same. Now suppose that I'm gonna use 10 and we have here 300 Kelvin. It is the same temperature of the air duct. Now initialize. Okay, then run calculation again. Let's see what's gonna happen if I increase H, or if I add convection transfer but at the same free stream. So gentlemen, as you can see, nothing happens because there is no heat transfer, because the free stream is still 300 Kelvin. Even if I increase this to 100, let's see, initialize. Calculate again. Okay. Contours, it's the temperature. Nothing happens. Nothing happens because the free stream, this is 300. So it is like the wall temperature. The wall temperature is 300 because of the air temperature 300. That's why there is no heat transfer. Okay, there is no heat transfer. Now we're gonna follow another strategy. Make it 10 again, and then we're gonna increase this to 308. We're gonna increase the free stream temperature. This means that the air that hits this surface has a temperature of the value of 308. So let's see what's going to happen. Wow. Remember the temperature. We use 308 for the free stream that hits the outer surface, while the air duct has the same settings or the same conditions. Now we have here an increase is 304 Kelvin, okay, at 10, at H equal 10. Okay, why? Because the heat of the temperature of the free stream is higher than the surface. That's why the surface now is heated. Okay, and it heats up, while this will, the air now, this air duct will start taking some heat. It enters at 300 Kelvin, but because of the contact with the aluminum, it will heat. Okay, that's why now we have here values, high values. So this is one. This is the when we increase the free stream. What if we increase now this to 100? So remember that we have here maximum at 304 at 10. Okay, now we have 304 at 10. Now we have h equal 100. What's going to happen? Well, 304. Now we have 307. Now we have 307. So increasing h, if the free stream is higher than the air duct temperature, increasing h will increase the temperature of this surface. So from 10 to 100 we increased the temperature of this surface, but this temperature, the free stream temperature, must be higher than the air duct temperature. Now if we make it 5, remember that at 10 we got 304. So initialize. Okay. Short run calculation. So we have here 303. So we decreased the temperature by decreasing the H value, but remember that the free stream is higher than the air duct. Here is enters at 300 Kelvin and here is 308. So this is pretty amazing. Okay, now what if we have this 10 and this is 292, okay, which is less than the air temperature. Initialize, and we have here h equal 10. So let's see again what's going to happen. So this is wonderful. Now we have these values. So we have this is 296. Okay, 296. Why? Because this air enters at 300 Kelvin, while this is at the free stream temperature is 292. So the heat transfer occurs from the air duct to the aluminum. So the aluminum is lower in temperature, but it starts to increase. Okay, so now we have 296. Remember that the free stream is at 292. Now increasing this h, so what's gonna happen? Now we have, remember that we have 296. So what's gonna happen if h increases? Increasing h. Well, increasing h now is the reverse. It cools down the surface. It cools down the surface. as you can see, this only happens if the free stream temperature that hits the surface is lower than the fluid. Okay, this is pretty interesting. So now we're gonna decrease it to 5. Let's see what's gonna happen. We have 293. Let's see. At 10 we got 296, and now we have 293. Now increasing it, we have here 297. 297. Why? Because we decreased H. So decreasing H here increases the temperature. It is the reverse process. Okay, so this is the reverse process. So mainly it depends on, remember that at 10 we got 296. Increasing H decreases the temperature, and decreasing it increases the temperature. Okay, we have 5 and then 10 and then 100. So you always focus on the free stream temperature and the temperature of the fluid next to the solid surface. Really, this is very interesting because we always depend on the equations to understand the behavior of the heat transfer. Okay, so now I'm very interested in doing the same but using the steady state thermal. But actually, before we start this, there is an important question. Can we use the heat flux in Fluent plus convection? No, we cannot do that, as you see, because you only can select one option. So heat flux to add heat to the surface, or by convection, or to give the direct temperature of the surface, or to combine between the convection and the radiation. Okay, it's mixed. If you wanna use the heat flux plus convection, you have to use the solar load, and I uploaded another video or previous video how to use the solar ray tracing. This is the only case I know so far to use the heat flux to hit the surface plus adding convection. And as you know, and as we have just seen, the convection, it depends mainly on the free stream temperature and the fluid next to the solid. Okay, or if we have two solids, I did not do that before, so you have to try those things, or mainly depends on your case study. Okay, so now we're gonna share the geometry. It's the same geometry we have here, the model. Okay, I'm gonna just reset the setup because I did it before recording. Okay, just hold on. It's busy. I'm gonna open the model. And I used the default material, structural steel. So now we exactly know what happened in Fluent. Okay, so let's see. Here I'm not gonna use the air duct because we do not accept here fluids. There are solids, structures, trees. That's why I suppressed the air duct. I do not have to define any fluids here, just solid. So we have here the initial temperature 2020, just initial temperature, the ANSYS setup. Number of steps is just one, current step, okay. I'm not gonna do anything. We have here generated the mesh, just sizing. I made it. You can make it fine, and we're gonna add convection. Okay, it is the same thing we did in Fluent, but now we're gonna see the effect of the convection here. Be careful what per square meter C is gonna be 10, and now the free stream is gonna be 300 Kelvin. You know, it is 27 Celsius, the same conditions. Okay, so now we added convection, and I added actually insert thermal temperature, so I added temperature before. Okay, so let's solve. Let's see. Now remember that we only have the aluminum. We only have the aluminum. Suppose that I only have the aluminum and I do not have any other thing. Okay, so the temperature is 27. 27. Why? Because it is the same temperature of the free stream. Now increasing this to 50. So increasing H here, notice that it's still 27. It's still 27. Okay. I'm gonna decrease it to 5. So it does not change. Okay, so increasing or decreasing, it is 27, does not increase. So suppose that we have 39 at 10. Solve it. So now I have 39 at 10. So increasing this H, it does not change. Okay, so because we do not see any changes, now I'm gonna add convection again to the back of it. It actually plays the role of the air duct in Fluent. Okay, we're gonna make it just maybe 10 at the 27. Okay, remember that we used 27, and now we're gonna make it 27 here with 10. Okay, so let's start from scratch. Let's see what's gonna happen. It's 27. No heat transfer. Okay, so this is 27. Now increase this to 50. Let's see what's gonna happen. The free stream for the front surface and the back surface are the same. Doesn't happen anything. Okay, 35. So now we're gonna put 335. Let's see what's going to happen. Oh yeah, this is what I needed to see. The heat transfer occurs, and there is a difference between, even if there's a slight difference, but the heat transfer started to occur. Okay, so we have here convection at 35, and we have here this is 27. Both H are at 10, but here because the free stream temperature is higher, it will heat the surface. Okay, now let's make some changes. Let's increase this to 50. Remember that when we increased the H in Fluent, the temperature of the surface increased. Here is H. So the 3662, and here is 33668. So the surface temperature here increased. Okay, so the surface temperature here increased. Okay, it was 1, but now it increases. Why? Because of the heat transfer, or the 27, and here is 10. Okay, so now let's make it 5. Make it 5. Oh, decreases. It decreases. Okay, 666, 668. However, it's still, this is higher. Okay, why? Because of the 35 Celsius. 35 Celsius. Also, even if this 5 is lower than H. Okay, so this is pretty amazing. Okay, now we're gonna make it easier, or let's see if we decreases this to 19. We'll have here 10. So as you can see, what happens is that this surface now is higher, has a higher temperature, of course, because this became 19 and here is 27. Okay, at 10. So this is pretty amazing. If we increase this, what's going to happen? What happens is this still higher. This still higher because of the difference between the free stream. Okay, even if this increases, it will not highly affect that. If it is 5. So as you can see in Fluent and here in ANSYS Steady State Thermal, it mainly depends on the free streams or free stream temperatures for the right and the left, and the heat transfer coefficient. It is a mechanism of the heat transfer by convection, and we have here still 24,332 and 24,334. Okay, so this is what we want to see. Now I'm gonna make it easier. Suppose that we only have this aluminum, and I'm gonna add just heat flux. Now we can add the heat flux plus the convection, no problem. But in Fluent we cannot do that. 500. Okay, just solve it, and we have here the convection. Make it 10 and make it 27. Okay, let's see the effect of adding a heat flux, and then we change the H again. So we have here 77. So we have here heat flux, and here is convection, and the temperature is 77. Okay, we're gonna now make it this 50. Now increasing H, will it increase the temperature or will it decrease it? We got 77. And we have 37. So increasing H at the same flux decreases the temperature. This means that the heat is swept, okay, from the surface. It is rejected from the surface. This is after increasing H at the same temperature, at the same heat flux, and decreasing it, of course, will increase the temperature. This means that the convection is not affecting the surface significantly. As you can see, it increased when we decreased the convection. But this is only if the heat flux is fixed at the free stream is fixed. Now, if this 10 and we decreased this, the temperature, of course, will decrease. You know, the free stream is very, very critical. It's a very important factor. That's why lots of people have very big confusion. We have here 69. We have here 69. Okay, if we increase this to 45, the temperature, of course, will increase. So, of course, it's 95. So, gentlemen, this is it. It's a very important technique to understand initial temperature, just the initial temperature. You can investigate it if you want. So, in this video, we actually investigated the effect of the convection in Fluent and in ANSYS Steady State Thermal. Again, if you wanna use the heat flux plus convection, you have to use the solar ray tracing, because you cannot choose here. Let's open again the wall, thermal wall. Only heat flux, temperature, convection, radiation, or mixed radiation plus convection. It's only radiation, and here is convection. You can use both. Okay, if you wanna use the convection and the flux, you go to solar ray tracing in the radiation, and I have a full tutorial about that. Okay, so I wish this helps you. I hope this helps you and kills any confusion. This is it. Thank you very much. Wassalamu alaikum.